Hello all, Dr. Shane back. We are approaching our last few labs, and this one, okay, as usual, this is my rough draft, making some notes on here. This is the buffer lab. Now, most of this lab is actually calculations. So basically what you want to do with the pre-lab for this one is come into lab with the calculations already done, and then what you're going to do is the preparation of the solutions for the buffer and prepare the buffer. And if we have time, we're going to go through adding some strong acid and strong base to this. Okay, so in addition to a calculator and this lab handout, you're also going to want your OpenStax textbook. And there's two appendices there that are going to be really useful. Appendix H and Appendix I. So if you go to the textbook and scroll down the table of contents on the online version of the book, you'll see tables for, I forget what they're called, like ionization constants for acids and ionization constants for bases. Those are sometimes called acid dissociation constants and base dissociation constants. That's probably what you called them in lecture, just so you know those are the same thing. So you want that available to reference, and I have the computer up here for that. Okay, so I'm going to erase most of what's on the board here in a little bit, but I'm going to fill in some information. But I want to explain the big picture. This video could be a little long, but if you do the calculations before you come to lab, then you'll be set. In fact, this could almost be done as a dry lab, which may be done in some cases depending on where the rater rest day falls, or if somebody needs to be quarantined. Okay, anyway, so let's get going here, and I think we're good. All right. So so we don't lose the forest for the trees here. This is a fairly complex set of calculations. And those of you that are moving on in chemistry, this is a procedure you're actually going to do again when you take biochemistry. So if you think about it, keep your lab notebook, don't throw it away, and then maybe we can archive this video, or you can bookmark it for future reference if you're going to take biochemistry someday. Okay, so here are the three big questions, and I'm going to answer all of these questions by using the example that's laid out for you in the handout. Then I'll get to that. So the first question is, how do you know what buffer to choose? Usually what you have is you have some target pH in mind based on the system you're analyzing. Seawater, some human tissue, or some experiment where you want to hold the pH relatively constant. Now, that depends on what kind of field of science you're in, but this is a fairly common thing. So how do you know what buffer to choose for the pH that you're trying to target, or the system you're trying to target? Okay, then the next question is, once you figure that out, how do you prepare the buffer? Now we're going to get into this a little bit more. So a buffer, qualitatively, is a solution that resists changes in pH, and we're going through all the math for why that is. Chemically, it's a weak acid combined with its conjugate base. So you prepare two solutions separately and physically add them together, the acid and the base, and you have a buffer. So it's a weak acid and its conjugate base, and we're going to show three examples. So what concentrations of the weak acid and what concentration of the conjugate base do you need? Then it turns into a solution prep problem. Because once you have a molarity, that's a concentration. Once you know the volume you're trying to prepare, and in this lab, you're either going to prepare 150 milliliters or 200 milliliters based on what your instructor tells you. So your total volume will be either 150 mils or 200 mils, so 0.150 liters or 0.200 liters. So just so you know that. So what concentrations do you need? And then you go into the lab and do the appropriate solution preparation. And then the last question, which is one, I'm not sure we're going to get to this one in lab with an hour and a half. That might be kind of tough. Is when you add a strong acid, so one that completely dissociates, or a strong base completely dissociates and gives you OH minus, neutralizing acid. How does that extent, to what extent does that affect the buffer's pH? Okay, so those are the big ones. And again, it's the the answer is it shouldn't affect it much. All right, so pre-lab questions, and these may not make a whole lot of sense right away. Number one, repeat the calculations. The handout sets up a problem really in its entirety, and I'm going to probably just go through that with you. If you know how to do it, you can just read it and get the answers that are shown here. Just do it on your own. If you don't need to watch me do the math, then don't do that. So repeat that one. So I think most of these, the lab manual sort of sets up the math and says, it can be shown that you'll get this answer. So they give you the answer, but don't show you all the intermediate steps. Show all the intermediate steps for all of the calculations. I think it's, yeah, okay. Anyway, so it'll do that. And I'm going to go through it, but obviously I'm not all that organized on how I'm going to do it. I'm just going to go through it. All right. The next one is sort of cataloging some data. I'm going to give you something, and I'll help you with this one too. Determine all relevant Ka values. So these are all acid dissociation constants, and you'll need the appendix A, or with H and I. So appendix H and I, we'll actually need appendix I for a reason that I'll show you in a minute. Determine the relevant Ka values, so you look them up, and then calculate the pKa. What's that mean? The prefix P means negative log. So you would take the negative logarithm of the Ka you look up, and I'll show you an example. For all of these buffers, I'll show you. Then the big one. This is the big one. This is one that's going to take a while. After we go through all these examples, your instructor will give you a target pH. Your instructor will give you a total buffer concentration, just like the pre-lab, or the lab manual, and will tell you what volume, 150 mils or 250 mils, and then you repeat all these calculations. So determine the appropriate buffer system, determine the concentration of acid, determine the concentration of base, and then do your solution prep calculations. We're going to save the changing of the pH for maybe a little later. So this video is going to get a little too long if we do that. So that's going to be kind of maybe we'll do that in lab. Okay. So I'm going to need, so make sure you write down, these are your pre-lab questions, even though they may not make complete sense right now. So take down all of this information on this board and this board, and make sure you have that, because I'm going to need to erase this. Okay, you're going to need some data. If you prepare solutions, you're going to need things like molar masses and concentrations if it's a stock solution. So I just want to give you the information. If you make an acetate buffer, let's see, where is it? So, yeah, so the acetate buffer, I should have goggles on. The acetate buffer, you're going to use acetic acid, okay, and the symbol for acetic acid is C2H3O2. That's the acid. Its conjugate base is going to be sodium. Okay? Now here's the deal. So this is the weak acid. This is the conjugate base containing the acetate ion. Sodium is a spectator ion. So we're going to use acetic acid and sodium acetate to make this, but you need some information. So this is actually sodium acetate trihydrate, and the molar mass of that's what's in here. So you'll have a little vial of sodium acetate trihydrate. The molar mass, just saving you some time, is 136.08 grams per mole. So once you have a molarity, you're going to need that to figure out how many grams of solid, because it's a solid, so you're going to weigh out some number of grams to make the molarity. Fine. The acetic acid is actually a very concentrated aqueous solution, and again, I brushed up, it's not, and this is how it comes from the company, and it's almost syrupy, it's so viscous. And the concentration there, I just want to double check, yes, is 17.4 is the molarity. That is probably the biggest molarity you will ever see in this class. Okay, so what's the point? So the acetic acid solution will be prepared via dilution. M1, V1 equals M2, V2, and V2 will either be 150 or 200. The sodium acetate is a solid, so you'll prepare that by using a solid. Take the molarity times the volume to get moles, then you take the moles times the moles times the molar mass, and that will give you grams. So that's solution prep. The phosphate buffer. Okay, the phosphate buffer, I put that in quotes because it's not exactly, it's actually two solids, two different solids. It's interesting. One solid is the acid, the other solid is the base, and I'm just going to put these two down here. So the first one, and this one is actually the base. Let me give you the acid first. So in this case, and I'm going to explain this later, the acid is going to be K, potassium, spectator, H2PO4, and the sodium acetate is a solid. By giving you a molar mass, that's kind of by default. The KH2PO4, it's a solid, has a molar mass, interestingly enough, almost the same as sodium acetate trihydrate. I didn't even notice that. Yeah, 136.08. And the molar mass here is, never thought of that, is 136.09 grams per mole. That's the acid. The base is actually K2HPO4. Again, potassium is a spectator. So this is going to have a -1 charge. This one's going to have a -2 charge when you take away the spectator ions. Can't forget all that stuff. And this has a molar mass of, 174.18. So when you do the calculations over here, you'll get two molarities, one for the acid, one for the base. And there's no dilution here. You use the same solution prep calculation. So that's the phosphate buffer. The ammonia buffer is a little different because, well, the acid is ammonium, NH4 with a positive charge is actually going to be our acid. But it's NH4Cl, ammonium chloride, and there's no hydrates here, or here. Only up here are there hydrates. And the molar mass is 53.49 grams per mole. 53.49 grams per mole. And then the corresponding base is actually ammonia in an aqueous solution. Again, this is, I don't even want to, this is really, why don't we use concentrated ammonia? It has that concentrated ammonia smell, if you've ever smelled it, but it's super concentrated. We may not even use, the ammonia in lab because it's kind of a hassle to handle. So we'll see. So your instructor may not even use the ammonia buffer. And the concentration of the ammonia is, you can see it's a solution. It's also very concentrated, is 14.8. So molarity is 14.8 molar solution. So you need all of that data to do your solution prep calculations, which I'm not going to go over in their entirety. All right, so I'm going to leave that there for now and erase all of this. What I want to do is you can start doing this if you want to. I want to start cycling back. I want to go through this entire example here and set it up. All right, so while you're waiting, on table Appendix H, if you can find the Ka for nitrous acid, so not nitric acid, you won't find a Ka for that one because it's a strong acid, it's essentially infinity. For nitrous acid, go ahead and find that while I'm fumbling around here. And hopefully I'll remember what these pre-lab questions are. I'm going to leave that there for now. Okay, I'm going to kind of whip through this. You can stop the video if you need to, because I'm just doing what it says here. So this is an example of everything you'll be asked to do. So you're talking. Oh, I'm sorry. I'm on paragraph 3. If the researcher needs, so you're making a total volume of half a liter. So again, you're going to do either 150 milliliters, 0.15, or 200 milliliters, 0.2 for yours. So this is just an example. And so the total volume of that, the total buffer concentration is 2.50 molarity. You'll be given that, and you're trying to do a pH. Your target pH is 3.00. So that's your target. And this is all information you'll be given to do the calculations on your own. Okay, so there's a part that's skipped over here. So what you're doing with this one, you're assuming you're going to use nitrous acid. You're just told that. And the symbol for nitrous acid is HNO2. The base for this one, remember how this works, so maybe I'll do an example over here, is going to be, I forget if it's sodium or potassium. Let's double check here. Oh, we're using potassium nitrite. Fine. All right, let's do a little bit of background information here. So nitrous acid is a weak acid. Fine. So it's, if you write the equilibrium for this, it's a weak monoprotic acid. And so this is the equilibrium. So this is the acid. This is the conjugate base. This should be old news. The Ka is the H plus times the NO2 minus over HNO2. And if you look that up on a table, and I just lost my table, here we go. Nitrous acid, the Ka, the acid dissociation constant, is 4.6. This is table H. 4.6 times 10 to the minus 4. I'm not really worried about units here. So the pKa would be the minus log of the Ka, because that's what P means. P means minus log of whatever that variable is. Okay. So I'm going to take the minus logarithm of 4.6 times 10 to the minus 4th. And just do that real quick. I already have it on my calculator. So, oops, I don't want that. So log of 4.6 exponential minus 4. Oh, I forgot to put the negative sign, but that's okay. These are always going to be positive. Now, I came up with 3.33. Your lab manual, or your lab handout, if you will, says 3.39. I'm going to use the 3.39. Now, why is there a difference? These Ka values are imprecise. It really depends on how they're measured. So you look them up in different tables, you might get a slightly different answer. I don't want you to get hung up on that. So I'm just going to assume instead of 3.33, just to be consistent with the lab manual, we're going to take 3.39. Fine. Now we're set. First off, why is this an appropriate buffer system? So takeaway number 1. So that first question, how do you know something is an appropriate buffer system? Well, you want the pKa to be plus or minus 1 pH units from your target. It is. Our target is 3. Our pKa is 3.39. That is well within 1 pH unit of our target. That's in general what meets what's called the buffering capacity. It will be an effective buffer for a pH of 3. If we had a pKa of 10, that would be a stupid choice. Or if we had a pKa of 1, that would be a stupid choice. So you want plus or minus 1 there. Fine. Okay. Excellent. And I'm going to kind of pull rank here. Let's figure out the pKa's. I think I said this in one of the other questions, so I'm not going in the right order. But since we've done this already, let's go ahead and get the pKa's of all the things you're going to use in lab. Sorry, this is a long video. So acetic acid, well, you can look that up, right? So acetic acid, and you can write the equation showing this dissociating and write the Ka expression. You can do that. So the Ka here is, what do I have? 1.8 times 10 to the minus 5. So the you can just take the pKa of that. Phosphate is a little tricky. So I'm just talking you through this. If you go down on the tables, you're not going to find phosphate written like that. You're going to find phosphoric acid. And if you notice, phosphoric acid has 3 different Ka values. Why? Because it's a triprotic acid. So, okay. So I'd like you to actually calculate all 3 pKa. So you'll have a pKa1, a pKa2, which is actually the one that's going to be relevant here. I'll show you in a minute. And pKa3. So you have 3 Kas. What does that mean? So phosphoric acid, everything here is AQ, by the way. This is just real quick, and you may have already done this in the lecture. So phosphoric acid is H3PO4. The first dissociation is this. So one of the H's comes off and leaves you behind with H2PO4. This would be the acid conjugate base pair. When it dissociates again, the conjugate base can still be acidic. Sounds ironic, doesn't it? And I just rewrote those in different orders. It doesn't matter. The H plus is given off, leaving you behind HPO4 minus. This is -1. This has to be -2. Oh, why do I say this one's relevant? Because take a look. H2PO4 is the acid. HPO4 is the conjugate base. This will be the relevant pKa for this one. So we're not going to use phosphoric acid, and we're not going to use the last one. But calculate it anyway. And the final dissociation, which is really difficult to do, you get the final proton, H plus is lost, and you're left with the phosphate ion. So pK2 is the relevant one. Fine. The last one is so get all 3 pKa's there. The last one's a little tricky for this reason. So in an ammonia buffer, ammonium is the acid, and I don't know if you've talked about this in lecture, so ammonium is the acid. And we write it typically in a slightly different way. We actually show it reacting with water. It doesn't really matter when it comes to the Ka. We could shorten this by just doing NH4 plus in equilibrium with H plus ammonia. But it's actually more physically relevant to show reacting with water, and these two are equivalent symbols for one another. Here's the problem. Ammonium, if you look at your table, you won't see ammonium in table H. You won't see it. What you will find is if you click on Appendix I, you will see ammonia. Okay, what does that do for us? This is just real quick. And I'm going to just kind of lead you down the path. So what are we trying to do? We're trying to find the pKa for ammonium ion. Well, if you look up this, you're going to find a Kb for ammonia. It's acting as a base. And the Kb for ammonia, NH3, is 1.8 times 10 to the minus 5. Do you know how to get a Ka from a Kb? I think you do. Ka times Kb equals Kw, which is 1.0 times 10 to the minus 14. Kw is a constant. Okay, so I'm just going to kind of sketch this out. So Ka is going to be Kw divided by Kb, and then get the pKa. So we have to do a little bit of work. So if you don't have the Ka for the acid, but you have the Kb for the base, you have to just go through a little bit of work. Calculate the Ka from the Kb, and then calculate minus log. So get all the pKas for all this stuff, and then that will let you choose which buffer system. Again, we're only using this acetate, ammonia we may not use, and then we're just using the second Ka2 for this one. Okay. Woo! Let's go through the math. And at this point, if you know what to do, and you follow the math on your own, you don't need to bother with this. So we have our data, we've determined our appropriate buffer system, and let's go back. Some things you can do. In the lab, for this example, you have a 10 molar stock solution prepared. So it's a pretty concentrated acid, so you have to do some kind of a dilution calculation. I don't know what the molar mass of KNO2 is. So the acid is going to be an aqueous solution with a molarity of 10. The potassium nitrite is going to be some solid. So before you get started, just say you have it, like you have that, get the grams per mole. And I'm not going to go through all of this. I'm just going to set up the math and let you carry it through. So I think we're set. And we know our pKa, we have it before, is 3.39. So if you want to just read the manual and repeat the calculations that are shown there, go ahead. I'm going to start and do all of that, but I need all this space. Except I want to leave this. And I don't need any of that anymore. Okay. All right, so let's do the math. Let's make some space and not be confusing. So the Ka equation is turned into what's called the Henderson-Hasselbalch equation. And I'm not going to derive that right now. It's not that important to do. I just want to see if you can get the math. So what we do is we take the Ka equation for a weak acid and we turn it into the Henderson-Hasselbalch equation. And here it is. pH which is your target pH, that goes here, whatever you're shooting for, is equal to pKa of the acid that you determined was plus or minus 1 of your target pH. So you've already determined this. Plus the log base 10, not natural logarithm, log base 10 of your base concentration over your acid concentration for whatever system you've identified as the appropriate one. So it'll be acetate over acetic acid, it'll be ammonia over ammonium, or it'll be HPO4 minus over, HPO4 2 minus over H2PO4 minus. So just make sure you have the right symbol properly. So what's the formula for the base? And don't bother with the spectator ions until you get to solution prep. We actually don't have to worry about it now with solution prep because we already have the molar masses. Okay, so great. So you'll do this math with your data. So in this case, the pH is 3.00, that's your target pH. We already figured out the pKa is 3.39. Fine. Plus the log, I'm just rewriting what's in the manual. In this case, the base, is the nitrite ion divided by the acid, which is nitrous acid. And that's all part of the logarithm term. So what do we do? Okay, I'm just going to put this up, I'm just doing the math. The procedure says that the concentration of the acid, plus the concentration of the base has to add up to the total buffer concentration. So this plus this has to equal 2.50 molar. Well, now we have two, we can do a substitution then. So we take 3, you can do this either way, but I'll just do it with the manual method. So 3.00 equals 3.39 plus the logarithm of 2.50 minus over, okay, I'm going to make this a little simpler to do the math quickly. I'm going to let X equal my HNO2 concentration. I think that's, is that right? Yeah. So rather than keep writing bracket HNO2, bracket HNO2, let's just make it simple. Let's simplify the algebra. So you want to make this 2.50 minus X over X. Let's turn it into an algebra problem right now. Can you solve for X? Can you do that? And then you get an answer, it says on here, you solve for X, you do all of that math, and you end up getting 1.78 molar. Okay, well let's just do this kind of quickly. So I'm not going to do the whole thing for you. So what you'll end up doing to solve for X, you'll take 3 minus 3.39, so that's going to be a negative number, isn't it? So negative 0.39 equals logarithm of 2.50 minus X over X. The inverse logarithm is 10 to that power. So this is going to be 10 raised to the power of negative 0.39. Hopefully I did this right. The answer is 1.78 regardless if I make a mistake. Equals 2.50 minus X over X. And I think you can take it from here, but I just want to make sure you calculate this. You can make this a number now. 10 raised to the 0.39 power. So, sorry about that. My calculator's not the greatest. negative 0.39. So 10 raised, you might use like the caret or something like that. Okay, I'm gonna carry like an extra sig fig. I'm not gonna worry about sig figs right away. I got 0.407 equals 2.50 minus x over x. Again, if I did it wrong, you get it right. And then you go the whole way down here, and I think you can solve for x, right? So you can multiply each side by x. So you get 0.407x equals 2.50 minus x. And then you bring this x over here, which is just 1. So 1.407x. Because I'm damn doing it for you. Equals 2.50. Let's see if we get the answer. So 2.5 divided by 1.407. Yeah, okay, that's what I thought. So x equals 1.78. All right, so you're welcome. I just did that for you. Okay, I think actually we can streamline this from now on. Fine. Yeah, that's the hard math. I don't know. Not necessarily that hard. So then you go through and you calculate, so what is that? Well, that's the molarity of the acid. Therefore, the concentration of the base is going to be 2.50, because that's the base right up here. 2.50 minus 1.78. And what's that end up being? 0.72. Nice. Okay, I'm not going to do the solution prep calculations for you. So what does that mean? That means you need to prepare one, 0.50 liters, because that's the volume you're trying to make. Well, you know what? I don't think I really need to do this, do I? The total volume is 0.50 liters. And one of them is a solid. So we're going to assume that the solid doesn't change the volume much. So you want to prepare half a liter of 1.78 molar HNO2 from a 10.0 molarity stock solution. It's kind of like the acetic acid one. It's concentrated acid and then the solid. I think that's right. But just generate the answer. What are you told here? Okay. The answer is told here. Looking on the back side here, it says some acids can be contained in their solid form, blah blah, stock solution. You can determine that you will require 89 milliliters of stock, so 89 mils. So your V1 should be 89 milliliters. So calculate that. And then you want to prepare a 0.72 molar, and what's the solid? KNO2. It's still 0.50 liters, and you're told it should take 31 grams. Nice. Okay, so then it becomes a solution prep problem. So what you want to be able to do in lab, and I think I'm going to skip for now, and if I have to make a supplemental video, you can keep reading, is doing the math if you change the pH with a strong acid or a strong base. I will make a supplementary video if we get that far. I'll check with the other instructors. With an hour and a half in lab, this is probably all we're going to end up doing. Okay, so what you want to be able to do That pre-lab question number 3, we'll kind of leave that sitting on the side. If you want to, I'll leave this as optional, you can go through the calculations for that part here. But this is how you do it. So you'll be given a target pH, you'll determine appropriate pKa, you'll be given a total buffer volume, and you'll set the problem up very much like this. You get an acid concentration, you calculate the base concentration, and then you do the recipe for solution preparation. So this is mainly a dry lab that you'll come into the lab, prepare it, check the pH, and see if you hit it. Did you hit the target of 3 in this case, or whatever it is? All right, so that's all we're gonna do. Long video, but I think it'll be really worth it. Buffers are super important. All right, that's all, and we'll see you in lab.